So today we're going to talk about mean value theorem for intervals. I think so. This is different from mean value theorem for derivatives. Remember, we have mean value. I think you saw this in count one that in maybe analysis one. Sorry, that if you have a differentiable function, then from A to B, so this is F. Then there exists a C between A and B, so that F prime C is Fp minus Fa and divided by B minus A. So the slope of the tangent line is the same as the slope of this secant line. That is for derivatives. The mean value theorem for intervals as the following. So it says that if F is so here's a definition. Sorry. So we suppose F is integrable, then we say that the average value for F on this interval is the interval F and divided by the length of the intervals. So F bar here. So sometimes for to make it clearer which intervals we are looking at, we use this notation. So F bar and then the interval down here. So you can think of this as the average of the function because you take the area under the graph and you divide it by the length. In particular, when you have a constant function, say f equal to c, then f bar is that constant c also. So the mean value theorems for integrals state that for continuous function, the average value of the function. So there will be a c, so that fc is this quantity. So this is actually easier to prove than the mean value theorem for derivatives, because later on I will show you why it is easier. But here is a proof, which is quite simple. So if f is continuous, then there must be, we know that it attains max and mean somewhere inside the intervals. So there are points B, P, and Q, so that Fp is a minimum of F, and Fq is a maximum. Okay. So this is called the extreme value theorem. Right? And if you look at the definition of the integrals, then this is one of the inequalities that we have last time, actually. So if f is, remember we have this, this is a consequence of the fact that if you have two functions, f less than g, then the integral of f is less than the integral of g. So here you take g to be this constant f. Then the integral is b times a times b minus a times n. Then you divide by b minus a, and you get exactly this part of the inequalities. And similarly, you get this part. So what is said here is that the average value of the function on an interval AB lies between the minimum and maximum of the function f on the same interval. Now, to finish, you just need to recall the intermediate value theorem for continuous function. It said that for any value between the value of f at 2 endpoints, then there's some point in between that attains that value. So the picture is this. So you have so inside the interval AB, so f may be like this. So this A and this B, and here is the point where is attained minimum, and here is the maximum. So if you look at this two values, it is a maximum, and you know that the average of f bar is between, so this is M and this is capital M, and f bar is somewhere here. So the average of f is somewhere in between. But the intermediate value theorem says that for continuous function between P and Q, any value that lies between Fp and Fq is attained inside that interval. So there'll be some point. So say this is f bar, then there must be at least one point where the function attains that value. So it cannot skip any values. And that is true for any continuous function. And remember that you need continuity because of, for example, if you have a function that is 1 here, so say this is 0, 1. And then you get is equal to 2 here. Then it cannot attain, it's never attained the value 3/2, for example. Even though 3/2 lies between 1 and 2, which has the values at the 2 endpoints. So that is that finishes our proof, which actually quite simple. Yes. So. Okay. Any questions about the mean value theorems? So later I will explain why it's easier to prove. So let's talk about indefinite intervals. So first we're gonna study the what is called additive function. So suppose that you have two functions f and capital F defined on the same interval, such that the derivative of capital F is f. Okay. Then capital F is called an antiderivative of f. So you have to notice what the n here is, because it's not unique. So you cannot say z antiderivative, because there are many antiderivative to the same function. So for example here, you can take f to be sine x, and capital F is minus cosine x. And sine minus cosine x, you can add any constant, so say plus 10. It's still an antiderivative of f. But it turns out that, yes, so here's a remark. You can add any constant in. So the remark, what is important, and we prove this, is that all antiderivative of f can be obtained from one antiderivative by adding a constant. In other words, any two antiderivative of f differ by a constant function. So that is you of f. So here we're going to prove this fact. But first, we're going to show an auxiliary lemma. So which says that if f is a differentiable function on AB, and such that the derivative of f is always equal to 0, then f is a constant function. So recall that one way is easy. Right? So if you go from if f is a constant function, then suddenly it implies that the derivative of f is 0. However, going the other way is not that simple. So I let you think about this for a minute or two, and the hint here is that the proof of this uses a mean value theorem for derivatives that I just recall at the beginning of the class. So if you you finish, you know how to prove, and let me know. Okay, anyone figure out how to do this? So the way we prove this is the following. So we want to prove that a constant, the function f is constant on AB, then you just need to pick any 2 points inside the interval and show that the value of f at those 2 points is the same. And if this is true for any pair of points inside AB, then the function f is a constant. So this is what we do now. So now we apply mean value theorem for derivatives to the function f and these 2 points x1 and x2. Then the mean value theorem for derivatives says that there be a point C, and so C is actually between x1 and x2. So that you have f prime C is equal to this quotient. But once you have this, you recall that the hypothesis is that the derivative of f is always 0. So f prime c is 0. And therefore fx1 has to be fx2, has to equal to fx2. Okay, so that finishes the proof of the lemma. Do you have any questions? Okay, so let's see how this implies the fact that any derivative of a function f has to differ by a constant. So suppose that you have two derivatives of f, capital F and G here. Then there is a constant c, so that for all x inside AB, gx is fx plus c. So we do this by apply the theorem. So to the difference of capital F and capital G. So you call H the difference. Then the derivative of H is, I'm sorry, this is a typo here, I think. So this two has to switch, right? This guy and this guy has to switch. So H prime is G prime minus F prime. And since there's a antiderivative of the same function F, H prime is 0. And now you can apply the previous lemma and conclude that H is a constant. And so therefore, because H is G minus F, you obtain that G is F plus C. Is this clear? Do you have any questions? Okay, if not, then let's continue. So because of, now we're gonna call the collection of all antiderivatives of f as an indefinite integral of f. So this is a collection of functions whose derivatives is equal to f. And because of the previous theorem, we know that these functions are differ by constant. So, so if you know that a function capital F is an antiderivative of f, then this collection of function is all of the form fx plus c for some constant c. So that is how we define indefinite integrals. So remember, this is a collection of functions. So this is not like the definite integrals that we defined earlier, which give you a number. So here's a couple of examples that I think you all know already. So for powers, so one thing you have to remember is you have two different formula when the power is -1 and different from -1. So when a equal to -1, so you have 1 over x, and the antiderivative is log x. And then for exponential, and Again, there's a special case that you have to exclude is when the a is not a is equal to 1, then you just have a constant function. So the alternative is x instead. So when a is not 1, the formula is here. So alternative of a to the power x is a to the power x divided by log a. And the particular case is when a equal to e. So recall that e is a number that log e equal to 1. So therefore, the alternative of the e to the x is e to the x plus c. And then here you have a bunch of other alternative formula for alternatives. And, let's see. So most of these are easy to check, but there are a couple of them down here that kind of actually not so easy to derive, to obtain the formula. But once you know the formula, it's easy to check. So you just need to remember this. Okay, so let's move on to the fundamental theorem of calculus, which connects the two concepts of integrals. And also, it actually more like a connection between the derivatives and integrals. So what the fundamental theorem of calculus say is that, so here is why it is useful. So first of all, it's give you a quicker way to compute definite intervals. So without using Riemann sums. And then it's also shown that integration and differentiation are inverse operations, so they cancel each other. And so you will see more clearly what I mean by cancel very soon. So first we define something called the area functions. So suppose f is integrable on the interval a, b. Then we saw earlier that for any x inside a, b, f is also integrable on ax. So if it's integrable on an interval, then it's also integrable on smaller interval. And then you define this function capital Gx to be the integral of f from a to x. So it is, you can think of this as the area under the graph of f, but only between a and x. So for each x, you're going to get a number. So if you look at all the x inside the intervals, then you have a function. So why we define this? So here, the next one, the first part is fundamental theorem of calculus, saying that the derivative. So this is a connection between the definite integral and indefinite integrals. So the area function is actually an antiderivative of the function f. And you can undo the definition of Gx and write a formula in this form. So here it means that you take the integral first, and then you differentiate, then you get back the function f. So see, gx is defined the way it defines as the definite integral of f for each x, and you have a definite integral of f, then the function that you obtain turns out to be an antiderivative of f. So in particular, it follows from this that the antiderivative of the indefinite integral of f is gx plus c. Do you have any questions about the statement of the theorem? Okay. So the second part of the theorem, so I think we're going to prove this later, but we state the theorem first. So the second part of the theorem said that conversely, you can. So here you can compute the definite integral of f using antiderivative of f. So integral of f from a to b gonna be capital fb minus capital fa, where capital F is any antiderivative of f. So now we are gonna. So so for example, well, I think we all know this already, but using this theorem is much easier to compute integral. For example, what we had before, I think. If you want to compute this, you only need to compute the antiderivative of this function, and we know from the table of antiderivatives, this is like 4/4 minus 3x squared. Or you can add any constant, but then when you evaluate from 0 to 3, that constant cancel, and then you get minus 27/4. So we did this earlier using the Riemann sums, but now if you know this theorem, then you can apply this, and it's much quicker to evaluate in intervals. Okay, so let's prove these theorems. So there's an example here. Okay, so I'll let you do this example first. So find the derivative of this function. Is a special function called the Fresnel function. Its name is not important. So find the derivative of capital S here. So when you finish, let me know. So has anyone finished? So I think I'm going to ask one of you to do this. You can say your answer. You cannot type it. No, it's not S0 minus S. X minus S0. What do you mean by that? What we want to compute is S prime of X. Right? So what is this? So this is the first part. Anyone finished? No, it's not 0. Why don't you try this? What is a so use whatever you have learned anywhere. So let's say you have cosine t dt. What is t prime? No, there are no minus x there. And it's not cosine actually. I think you are confused. Maybe I try to go back and show you the theorem. Also. Maybe because you don't have the theorem in front. Oops. So we have Sx is this. So find this. So here's a theorem that you need to apply. Because in this case, you cannot find the alternative, but this computes integral explicitly. So try to think about this, which function you should what function plays a role of f here? So do try to think about this. This is very important to understand this theorem. And when you finish, please let me know. Anyone figure out? So which function we should take for the function f here? What should our f be? No one knows. Maybe I will call one of you to have their opinions. So what do you think is fx in our example here? So can you answer 2, 3?
No, I don't have the answer.
So you don't know what you take for fx here. Okay. Thank you. So do you understand the statement of the theorem? Is the statement of the theorem here clear to all?
Rồi thầy Gia.
Let's see. No, fx is the one. No, fx is the one that we. What I mean is fx is. See, we are using this formula. Okay. So you have to figure out what f you are taking here. But all you need is so here is the derivative. Right? So this we want to find the derivative of this function. So it is the same thing as so ddx just stands for derivative. Okay. So ddx of this is the same as the derivative of this the one inside the parenthesis here. So what we have now is you just need to compare this with this. So what is f now? No, not from so fx. So you see, so this one should be ft, right? So if ft is sine of pi t squared over 2, then well, I don't know why you said from 0 to x, but fx should be sine of pi x squared over 2, because this should be ft. And if you change t to x, then fx is sine of px squared over 2. So x is just t and x is the name of the variable. So you can change. So that's just saying that if you know that fx is x squared plus 1, that is the same as saying ft is t squared plus 1. So if you change the parameter here, you change the parameter on the right hand side too. Is this clear? Do you have any questions? Any questions? No, the 0 and the x is the limit of the integral when you define the area function. Okay. So you see in here there is equal to. You take the and the integral sign disappear. Okay. Okay, good. So make sure you understand this. Really try to understand this. If there's anything you are unclear, then ask me now. Because if you don't understand at this point, then you just make it harder later on. Okay, so now if you agree, then this one, this is okay. Then what this is really is out the derivative of x is equal to this, and by this formula, it is exactly equal to sine sine x squared over 2. Okay. Is this clear at all? Okay, so let's seem you are kind of unclear about this. So let me give you another exercise and order. Second, someone. So let's so see when so let's do another exercise and so that you completely clear about this. So let's now define. So this may be a little bit more difficult, but so is this more difficult? I guess so. So I let you try this. So find S prime X. As well, do you need this formula here? Maybe I write it down for you. So the formula we have is that d over dx, that is the derivative integral from 0 x ft dt is equal to fx. Sorry. Okay. So try to compute S prime x when S is given by this formula. Okay. And let me know when you finish. So the function under the interval is t squared minus 2xt. So note that there is an x here, so 2xt. So I suggest first what you do to try first is that you try the same compute S prime, but for the function t squared only, and then you try this. So first you look at this one only, the t squared part. Answer. someone answer, but let me try to get this. So y fx is minus x squared. 2xt. It's not 2 times t, is 2xt. So it's the same x here. Okay? The answer is not correct. And I will explain later on. So try first this part. So let's ignore this part for a moment and tell me your answer, and then I will. So try to first you try without this part. So this with the 2xt here, it is a little bit tricky, but how it should be easy. So tell me the answer when the interval is from 0 to x dt. And when finish, so what is the answer when you do not have this part? You only have t squared as an integral. So you only have t square there, it would be simple, right? What should this be? What take now? So this must be ft, right? Yes. No, I think you got it incorrect. So let's first work out this case when which is t square here. Then ft is t square. So fx is x squared, right? So you apply the formula down here, then the derivative is x squared. Is this clear? Any questions? Okay, now I will ask you to do this. So let's say it is tq minus 2t dt. So what would be the derivative of this? So I assume you understand everything I said so far because you didn't ask questions. So now I will ask one of you to do this quickly, right? Gia Ân.
Yes.
Can you tell me the answer to these questions?
I think it's x squared minus 2x.
This is t cubed minus 2t, right? So
yes.
for these questions, what is the derivative of the
Sorry,
integral?
I
Can you say
cannot
your
hear.
answer again? Can you tell me the answer again?
I think it's x cubed minus 2x.
Yes, okay, thank you. Okay, that's good. Yes, so in this case, this is your ft, right? And by the theorem, this is fx, so this All right. So let's consider this case now. So what do you think the answer to this? So here you have 2xt here. So what do you think is the answer? So you again, Zain, what is S prime?
I think is minus x square.
So this is that because you replaced the t in here by x?
Yes.
Okay. Okay, let's try to figure out the answer. So you have to read this the statement of the theorem very carefully. So in this case, it's actually I don't think it's the right answer, and the reason is the following. The reason is the way that we define the function s, it should be of the form. To apply the fundamental theorem, it is 0x and ft dt. Okay. See, there is no x in here. This can only be a function of the variable t. Is that clear? In here you have x. Okay. So you cannot directly apply that theorems. So what you can do is use studies. So we know the answer to this part already, right? And now by linearity, you can just look at this and try to figure out what is this. And then you combine the two answers, right? I'm sorry, this is x here. So this is x, okay? But now x doesn't depend on t, so this interval the interval from 0 to x of xt dt is the same as the interval. So it x times 0 from 0 to x of t dt. Okay. So now you can either compute it explicitly, and I think you have to compute it explicitly actually, or you can differentiate this and use a chain rule. So what you get gonna be I think x cubed over 2, right? Because the antiderivative of t is t squared over 2. So you get the integral here is t squared over 2. And evaluate from 0 to x, and you get x squared over 2. And multiply with x, and you get x cubed over 2. When you differentiate this, so d dx of this gonna be equal to the derivative of this, and you get 3 over 2x squared. Okay. So s prime gonna be the derivative of the first part with t squared here, so that is x squared. It's minus 2 times the derivative of this guy, which is 3/2 x squared. So what you get is minus 2x squared instead. Is this clear? Okay, very good. If any of you find this not clear at any point, then please stop me. Right? And I will explain again. So the critical point, the important point is that to apply the fundamental theorem, make sure that inside the integral here, there's no x. If there's x, then either you have to find other way to do it. All right. So let's continue. So we're gonna. So here is an application of. So this is pretty simple. You find the area under the graph of x squared from 0 to 1. So this is our first example. Right? So we now just see how it very quickly follow from the second part of the fundamental theorem. So once you know that x cubed over 3, so this is from our table of anti-additive. You know it's an anti-additive. You put it here and you evaluate from 0 to 1, and you get it 1/3. So we also obtain this using Riemann sums, but it's take much more work, right? Here it's quite simple. Okay, so here is the proof of fundamental theorem, part 1. So that is a part that you want to show that the derivative of G is FC. The derivative of the Gx is Fx. So here instead of I think the proof is so let me explain this here. So what we want to show is that suppose that so Gx, oops, Gx is so Gx equal to the integral from 0 to x. So it can be a to x. It doesn't matter if you take a with 0. Now here you're gonna you want to prove that G prime x is Fx. But let's call we're gonna show this since we use a variable x somewhere else. Let me prove that G prime at the point C is equal to C for all C between A and B. So this is the same as G prime x equal to Fx, because x is just the point that you evaluate things. It is not important at all, whether you call it x or C. Now, and then you look at the definition of Z prime. What is this? This is, by definition, the limit when x go to C, right? Of Gx minus Gc divided by x minus C. Okay. So we have to show that this quotient is very close to Fc when x is very close to C. And you can see it quite clearly if you draw the picture. So C is the one that is fixed, and x is converging towards C from either side. So x can go from the left as well as from the right. here I draw for you from the right. And what is the difference between gx minus gc? So gx is the integral from 0 to x, and gc is the integral from 0 to c. So the difference is the integral from c to x of zt dt. I hope this is clear. Right? Okay. So what you have to do is, so this is the difference only. What you want is you divide this, right? Then you have to show that, oh, I'm sorry, this is ftdt. Right. So you have to show that this converts to fc, okay, as x go to c. Is this clear? Do you have any questions? So there is a epsilon delta proof in the slide, but you can see this also easily using what we have learned just now, is that this one is nothing but the average. So this is the average value of f on these intervals. And you know that it's obtained somewhere inside the intervals, right? So there's going to be a point, say y here, let's say. So therefore, this one going to be equal to fy for some y in between c and x. So this is equal to. So this is by the mean value theorem for integrals. So this is equal to fy for some y in between c and x. But now when x go to c, then certainly y is also go to c. So this is a squeeze theorem. Because so you have say c is this, and this one is fixed, and certainly it's go to c, and this one go to c, so y also go to c. And so therefore, since f is continuous, this one converts to fc when x go to c. Okay. Is this clear? Do you have any questions? Okay, so I guess you don't have any questions. So while we are here, let's prove also the second part is fundamental theorem, which state that. So the second part of the fundamental theorem is that if so this is a connection between definite and indefinite integrals. So if you know an antiderivative of f, and that is the same thing as knowing the indefinite integral of f, then you know the definite integral. It could be f from a to b, and that is fb minus fa. But this follows immediately from the first part. Right? because recall that if you define gx to be the integral from a to x, so this is the same a. Sorry, t dt. This is an area function, then it's an antiderivative of f, right? Because you know that g prime is f. So capital F and capital G are both the antiderivative of f. So therefore, they differ by a constant. So gx gonna be fx plus c for some constant c. So this is the theorem that we have earlier about indefinite integrals. All right. So now what is this? Because g is differ from f by a constant, clearly fb minus fa is equal to gb minus ga, right? But this is the same thing as the integral from a to b of ft dt, which is g of b, right? And minus g of a. But g of a is what? Is the integral from a to a of ft dt. And we know that this is 0. So the conclusion is that this one equal to this one. So we finished the proof of the part 2 of the fundamental theorem. Do you have any questions? Okay. So let's go back to the slide then. So okay. So yes. So here's the theorem. Yes, so you can look at this example. So by the way, this is what I meant earlier by the differentiation and integration cancel each other is exactly because of these things here. So you integrate the function f and you differentiate, then you get back the function f. So they cancel each other. And here is also a kind of the same thing. So since f is an capital F is antiderivative of f, you can rewrite this as the integral from 0 to b, a to b of capital F prime x dx. is equal to FB minus FA. So in other words, you can see that if you differentiate, then integrate, then you get back the function. So in both ways, you get back the original function. Okay, so let's look at the example here. So these are pretty simple. So this shows you that you can compute integrals more quickly now. So for example, here you have this function, and because of linearity, you can split into three parts, and you compute antiderivative each part separately, and you add them up. So the antiderivative of this, we haven't talked about that. But this function is this one, and then you evaluate from 1 to 9 when you obtain the answer. So it's much quicker, and you can imagine it will be painful if you use Riemann sums to compute this. Okay. So here's a trick questions. So what is wrong with this calculation? So you know that the antiderivative of x minus 2 is minus x minus 1, right? You differentiate this and you get x to the power minus 2. This one is antiderivative of x to the minus 2. And if you calculate, then evaluate from minus 1 to 3, then you get minus 4 over 3. However, you can see that on the left-hand side, you get a positive function, x squared is always positive. And you integrate from minus 1 to 3, so you should have something positive, to get something positive. But here it's negative. So what is wrong here? So tell me when you know what is wrong with this calculation. Anyone know what is wrong with this? Anyone? So what is wrong here is that this is an antiderivative of this function only away from 0, because they both, so 1 over x squared, it looks like this is let's go to infinity when x go to 0, and minus x to the power minus 1 would look something like this. Okay. So it is only antiderivative when x is not 0, away from 0. So if you take the intervals -1 to 3, then this is not antiderivative on the whole intervals and the function. And so you cannot use a fundamental calculus. And it's also because the function 1 over x squared here is unbounded like this. It doesn't have an antiderivative actually. On the whole interval here. There are no functions that can give you this because at 0 is not defined. So here is a example when you cannot use a fundamental theorem because function is not defined at some point inside the intervals. And later on, you will see that this is a type of improper intervals, and it turns out that this one actually equal to infinity. Is this clear? Any questions? Okay, so yes, you can see it here. All right, generalization of the fundamental theorem part 1. So remember the fundamental theorem is for the area function. So let me record here. So if you have S, we call it G. So G of x is integral from a to x of ft dt. Then G prime x is equal to fx. So that is what the fundamental theorems gave us. So it gives us this formula for the derivative area function. And now this generalization here is for the limits of the intervals. You don't necessarily have to have the lower here as a constant, and the upper limit doesn't have to be exactly x. It can be a function of x. And the same holds for the lower limit. You can make both of the lower and upper limits to be a function of x. Then there's still a very nice formula for the derivative of x. And you can also see that in the case of the area function is a special case when ux is always equal to a and vx is x. And since ux is always a, you see that in this particular case, u prime is 0, so this one is not here. And vx is as x, so v prime is 1, and so this one is exactly fx. So it gives us exactly the same formula as before in this particular case. However, this formula works for much more general intervals. So So let's see how we prove this, and then we go over some example. Yes. So here are the examples. So let's talk about, so what different from before is that, so notice the form of this. So it's pretty much like, so you have here two terms that are very, very similar. But the one that's corresponding to V takes a plus sign, the one with U takes a minus sign. But otherwise, they are pretty similar. So you evaluate F at the end points, Vx, and then you multiply also with the derivative of V. And the same for the other end, lower end points. But that has an extra minus sign here. So let's, I'm not sure if you can remember this formula. So let's, so the formula is this. So for you to do the example, so f prime x is f nu vx. So v is upper limit, v prime minus f as the lower limit. So try work out this as a formula for f and g as a relative of f and g in this example, okay? Using this theorem, this formula. So when you finish, let me know. Anyone finish? Anyone finish the first one? So here the function f is so ft. Okay. Cool. Okay. If you need more time, then okay. I give you a couple more minutes. Okay. Okay, so let's see. Yes, I think you are correct. Yes. So in the first example, ft is log tq plus 4. So now the answer gonna be f at the point x2, and then multiply with the derivative of x squared, so that is 2x. And then the last one is f at the point 3 times the derivative of 3, but with that is 0. So it is equal to 0. So all you left with is 2x, f at x squared. And that gives you 2x times log of x to the power 6 plus 4. Okay, very good. Anyone has questions? Okay, so how about the derivative of g? Anyone finished? Yes, very good. So it is okay. So here is your function. So now the variable is u. So this is f of u. So we have the du. So fu is tan of cosine u minus 4. So g prime gonna be f at the point 5 times 5, the derivative of 5, but this is 0, and then minus f at the point 2x times the derivative of 2x, which is 2. Okay, and so you get minus 2 tan of cosine 2x minus 4. Okay. Okay, very good. Any questions? If any of this is not clear to you, then let me know. Okay, so let's continue then. Okay, so here we now next learn several technique of integrations, and the most important one is chain of variables, or you can also say substitution instead. And other one is integration by parts, or partial integration. So let's talk about chain of variables. So if you have u is a differentiable function, then the integral of fu x u prime x dx is equal to the integral of fu du. So you have to interpret this as carefully, because writing is this way doesn't make much sense, because here you have a function in x, right? But here you have a function in u. So if you write like this, so for example, if you have u equal to x squared, what this say is that f of x squared times 2x, the integral of this equal to the integral of fu du. But then what you obtain is here is a function of u. So say this is g of u plus c. So you have found the integral of f of this function, the antiderivative of this function in terms of function in u. So writing it like this doesn't make any sense. So what this formula means is that if you know is that you have to use this relationship between u and x. What this really means is that once you know an antiderivative for the function f, let's say this is a f of u and cos plus c. If you know this indefinite integral of f, then you know the indefinite integral of this function. So now in the variable x, and this function may look much more complicated than this function. Okay. So the idea is to find, I don't know why this, is to find u so that first of all, fu, capital fu is easy to find, the antiderivative of f. And also, once you do that chain of variables, this one give you the function that we are looking for, the antiderivative. So somehow you reduce this more complicated integral to this less complicated one. One stroke like this. Okay, so what it means is this. Yes, so what it means is that if you know that capital Fu is an antiderivative of Fu, then the Fux, so when you compose this F with the function U, you get an antiderivative of this Fux times U prime X. But that is pretty easy to solve because all you have to do is you differentiate these things and see if Fux U prime X is what you got. And that is exactly what we will do. We differentiate this. Then we just use the chain rule, right? The chain rule says that the derivative of this is capital F prime at ux times u prime at x. But since the capital F prime is small f, this is nothing but f ux times u prime x, and that's all there is. So this is pretty easy to prove, and but this is very useful in practice. But usually the difficulty is to find an appropriate function u, so that this is exactly what you are looking for, u and f, so that this is what you're looking for. So usually you would be asking to compute an integral like this, and somehow you have to write this in this form with appropriate f and u, so that you can reduce to this easier interval. So let's look at a couple of examples. So here's this one example. So this look complicated, right? However, if you take f to be square root of u, fu square root of u, and u is x squared plus 1, then this is exactly fu times u prime, right? So u prime gives you 2x, and f of ux is exactly square root of x squared plus 1. So now all you have to do is find the alternative of fu and put in the relationship u equal to x squared plus 1. So so as I said earlier, this is not it's not quite make sense here, because this is function in x, this is u. So it at the end you have to replace this u by x squared plus 1 to get the function in x, then everything makes sense. So this is okay here. Okay. So let's continue with another example. Any question? I presume that you know this already. If this is the first time you see this, and let me know, right? Here's another example is to find alternative of x cubed times cosine x to the power 4 plus 2. So we just take u to be x cubed plus 2 and fu to be cosine u. But when you compute the u, you have 4x cubed dx instead. So this is another way of doing things. And so it's so another way is you find u, and then you rewrite everything in terms of u. Okay. So before, what we do is we guess the function f and u, and then you rewrite everything in terms of put it in and check that fu times ux give you what you need. Another way is you guess what u is, and then you try to write this integral in terms of u. Okay, so this is what we did. We are doing now. So if you guess that this u would make your integral simpler, then the job is to rewrite this in terms of u. And in doing that, it is very crucial in that you first look at dx and write this in terms of du and u. Or first is just convert it into du, and there may be some extra, but it's we take care of that later. So this is what we do. We differentiate u. So du is the same as 4x cubed dx. Remember, this is because du dx is nothing but u prime x, right? This is another notation for derivatives. This is, I think, the Leibniz notation. Oops. So du over dx is u prime, which is 4x cubed. And that means that dx is du over 4x cubed. So it's okay at this point to still have x here, okay? The key point is you have changed from dx to du, okay? So once you have this, so dx is du over 4x cubed. You look back at your integral, then you get x cubed, right? Cosine u. And then dx you write as du over 4x cubed. Okay. So the crucial point is change to du first, and then you deal with the extra x later on. So here you have 2 extra x, place where you have x, but then this cancel, right? So you get cosine u over 4, and the alternative is just sine u over 4. So always convert du first. And then you have to make sure that after that, you can take care of all the x in the integral, so there are no x left. So here is so the first step is converting to du here, and the next step is you take care of all the remaining x. So see, the key point is at some point you must finish with x. There are no x anymore. And once you that you find that you will u, and then at the end, this is also crucial that eventually you have to put x back in. So any questions about these steps? Okay, so let's continue. So here as a step, so you can. So usually it's from experience rather than you have to guess and use that it works. So there are a couple of rules that we will see later on that for certain type of integrals, there are certain chain of variables that is that works. But it's not always that you can find such a u and sometimes you have to use other method. So the next thing, as I said earlier, you have to calculate dx in terms of du, and that still may be x. But then you, after some manipulation, you have to get rid of x. So I guess this one is an easy one. So I show you the solution here. So you can look at this is a pretty easy example. So I will skip. Okay, so I let you do this. Okay, so let me know when you finish, right? So do try to follow the steps that I said earlier. Anyone finished? Okay. That's fine. I guess you will be correct. So what we do now is you try exactly like before. You put u to be x squared plus 1, right? Because that will somehow simplify the as a square root. As the next step is you rewrite dx. Right? Yes, that's a chain of variable. And because du is 2x dx. Wow. Okay. Then dx is 1 over 2x du. So you put this back in. So see, the first step is always make sure that dx becomes u, and then you deal with the remaining x. Okay. So you once you get this, you deal with this x to the power 4 later on. And now, since you have to get rid of this x, you have to somehow write x to the power 4 in terms of u. But that is pretty simple, right? Because x to the power 4 is x squared square, and x squared is u minus 1. So you get u minus 1 square here. And now I think the only thing you can do, I think, is to expand this u minus 1 square, and then you get a bunch of power of u, and then you just integrate term by terms. Because you know the alternative for a power, and you just apply this to this. And then at the end, what you have to do is you put back in the and you have to replace u by x squared plus 1. Okay. All right. Yes, I think you can also simplify. I don't know if it's simplify, but you can make a common denominator factor out, and then so you see that this is can write this as x squared power 3/2, and then you make common denominator here, something 105, and then inside you would get 15 x squared plus 1 squared, right? And minus let's say 42 x squared plus 1, and then plus 35 and plus c. And then you can even expand this to get 15 x to the power 4 minus 12 x squared, and then plus 8 for the bracket. So let's see. Yes. Okay, so one of you did this. That's very good. Okay, so let's continue. That's so good. Yeah. So now we let's move on to substitution for definite integrals. So if you have a definite integral, so that is one with a and b here, then the key point in so when you do chain of variables, this and this is pretty much the same as before, like for indefinite integrals. The key point for the definite integral is that when you do chain of variables, you have to change the limit as well. So since u is a function of x, right? When x equal to a, then u is equal to u at a. And similarly, when x is b, u is equal to u at b. So you have to replace this limit accordingly. And the proof of this is still as simple as the one before. I don't think we have a proof here. Okay, so let's just work on this example, for example. So try to compute this. Anyone finished? Yes, very good. So u is 3 minus 5x. And then you replace dx by minus 105 du. And then you work out the limits, right? And x equal to 1, then u is minus 2. X is 2, then u is minus 7. And so you obtain this. And the antiderivative of so minus 1/5 outside here is because dx is minus 1/5 of du. And then you just have an interval in the in u, and the antiderivative is minus 1/5 u. And so the answer is 1/14. Okay. So okay. Yes. Just okay. We will see as an example later, because now we're going to talk about integration by parts. Sometimes it's called partial integration. And so the formula is this. So this is a formula for you to for the ease of memorization, but it's by itself it doesn't have much meaning, because here u and v are differentiable function. So it is a function of a variable x, of the same variable. But remember, we haven't defined what this means by this, right? So we have defined the integral of a function in terms of a variable, but what is meant by u dv we haven't defined yet. So what this really means is that this you have to think of as the integral of ux times v prime x dx, because again, this is what we use several times already. So this is the same notation for vx, right? V prime x, sorry. And now you multiply both sides with dx. So this is very formal. Oops. You multiply both sides with dx, then what you get is dv is v prime x dx. So that's what we replace this dv with. And then u is just ux, right? So that is the way that you have to interpret this, what this means by this two integral, what this two integral means. And this formula is just there so that it's easier to memorize, okay? So, so this is here. And this is one example of this formula. When you have u is x squared and v is sine x, then what you get is this integral. So integration by parts. So what this really means actually is, so this one, what this means is that the integral of ux v prime x dx is ux vx minus integral of vx u prime x dx. Okay, so that's what this formula means. Now the proof is pretty easy actually, but this is really a very important technique of integration, by far the most important actually, together with substitution. And the proof is simply by the product rules. When you differentiate u times v, then you get this one. And now you integrate both sides. So the integration, I mean, taking antiderivative, taking an indefinite integral at both sides, and you know that the antiderivative of this is clearly ux vx plus c, right? And so it's equal to the sum, the integral of the sum of u prime v plus u v prime. And now you change the sign of these terms. So you just move what you're gonna move. So you move this term to this sign. So this term here. Then you obtain this. Now the C here disappeared because in both sides there are integrals, and for each integral there's an indefinite, undefined constants. So this is okay. It's not okay. In here you cannot erase this, because here you have an arbitrary constant, while on the left hand side you do not have it. So you must have C here. But once you move one of the integral to the other side, then you don't need this C anymore. Okay. So usually what you would do is find U and V so that this is equal to what you want to compute, and also it has to be in such a way that this one is easier to compute. Okay, so somehow you have to reduce the difficulty of the problem. So let's do this example here. So trying to find U and V so that UV prime is exactly what we have here, x sine x, and V U prime is something simpler. So if you find U and V, then let me know. Right? Sorry. That's something. Yes, that's right. So U is x, and that's right. U is x, and V is cosine, minus cosine x. And that is because, so if you guess U, then you have to find V so that V prime is sine x, right? So so you get V is minus cosine x, and then you apply the formula, the integration by parts formula. Then this is uv prime or udv, and this is u times v x minus cosine x. This is u times v. So this is udv, and then this is vdu, and you realize that vdu is now cosine x only. And the alternative of that is sine x plus c. Okay. So just notice that from here to here, you see it's simpler because from here to here, simpler because this x disappear. Okay, let's continue. Yes. So for this one, find u and v, and let me know your answer. Yes, you miss plus C, but it's okay. So this is already in the, yes, UDV form, so you don't have to do anything actually. So U is an X and V is X. And get this. And so VDU gonna be just 1. All right, so since we are here, let's do something similar. So try this. Say x to the power 10 log x dx. So let me know when you finish. Anyone finished? Okay. I guess the answer is a bit long to type. Yes, so there is so one way to do this is you try as before. You leave this alone. So this is u and your v is still x. Then what you get is, so this gonna be u times v, so x to power 11 log x, and then minus v du. So v du gonna be x times the derivative of u, that is 10x to power 9 log x. Then what? Plus x to power 9. Because the derivative of log x is 1 over x, so this is dx. Okay. And now you distribute this x inside. What you're gonna get is inside you get x power 10. Okay. So you realize that one part of this is easy to compute, right? So minus of x power 10, the antiderivative is minus x to the power 11 over 11. So I will erase this. Okay. So what we're left with is this one. But this is exactly what we start with. So this is, so if we call this I, then this is minus 10I. So I can write this. So I move to the other side, then it follows this one here is exactly plus C is exactly 11 times I. So now you divide both sides by 11, then you get the answer. Yes, your answer is correct. Yes, so now you divide both sides by 11. Then you get here you become 11021. And you can still call C over 11 C. It doesn't matter, because C is a constant. Okay. So that is one way. Another way is you maybe quicker is that you keep you write this as so I will write this for log x and d of x to the power 11 over 11, because that would give you exactly x to the power 10 dx, right? So this is u and this is v, and so this equal to x 11 over 11 log x minus v du, and so v is this and du is 1 over x. So what I get is x to the power 10 over 11 dx, and this is simply x to the power 11 over 121 plus c. So this is equal to this. This becomes this. Right. Okay, very good. If you have questions, stop me. So let's continue. Yes, let's try this. Let me know if you finish. You may not be able to type the answer, but just tell me if you finished. Yes, I think you get it right. So what you do in this example is you have to do integration by pass twice. Okay. So how we do this? First, you let say u is sin x, and v is just e to the x, right? And so u dv v du gonna be e to the x cosine x dx, because derivative of sine cosine. And now you realize that you get by almost like what you start with. So you may think that this is not gonna work. However, if you continue, integrating by pass, sorry, this is not so you integrating by pass once more, then what you get. So we're going to deal with this alone. So you're going to look at this integral here, e to the x cosine x. For this, you do the same thing. V is still e to the x, and now u is cosine x. And if you do that, then what you get is e to the x cosine x dx equal to u times v, so that is e to the x cosine x, and minus the integral of minus sine x e to the x dx. Okay, so this minus sign cancel, right? So you can make it plus. So this explains the square brackets on the next slide. So this integral now, I replace this by e to the x cosine x times this plus this, but this is exactly our I. So let's go to the next slide. So what you get is, yes, so this is what we just compute. And as I said, this is exactly I, this part here. So when you break the brackets, what you obtain is I equal to e to the x times sine x minus cosine x minus I. So now you can move this I. So because of the sign here, you can move to the other side. And of course, when you do that, you have to add in constant c. And then you divide by 2 to obtain the answer. Okay, very good. Any questions? So usually that's what you have to do with the product of e to the x and sine x or cosine x, for example. Okay, so let's see. Okay, I think we can stop here for today. Do you have any questions before we stop? Okay.